Imagine a world full of tiny machines that perform complex processes inside our bodies. Imagine that they can move in an ordered and controlled manner that constitute a nano world fueled by chemical and light energy. Well, this dream is not far away. Jean-Pierre Sauvage, Sir Fraser Stoddart, and Ben Feringa won the Nobel Prize in Chemistry in 2016 for developing these synthetic molecular machines. So what are molecular machines? Molecular machines simply are tiny components in the nanoscale level that can assemble and function in response to external stimuli. These synthetic molecules mimic the biological systems that utilize the chemical energy to make linear or rotatory motion within the body. A wide variety of biological functions can be performed using this harmonic motion, such as muscle contraction, intracellular transport, and ATP synthesis. So now, when was the idea for synthetic molecular machines developed? Let me tell you. The story had begun in 1950 when scientists were proposing the concept of mechanical bonds. These kind of bonds can give rise to molecular assemblies in which the individual parts are not covalently bonded but linked together in an entangled fashion. However, the experimental synthesis had not been achieved at these times. In 1983, the field had a giant step in Louis Pasteur University in France when Jean-Pierre Sauvage and his co-workers succeeded in creating a template synthesis for these interlocking molecules. They used copper ions to interlock two ring-shaped molecules, and then the reaction progresses to synthesize chains of these molecules. This actually opened the era for topologically challenging structures. Then another breakthrough was accomplished in 1991 by Sir James Fraser Stoddart and his colleagues at the University of Sheffield in the United Kingdom, where they managed to synthesize another mechanically interconnected assembly that can move in a translational way. The researchers utilized an electron-poor aromatic entity and electron-rich one, and through the attraction between them, the poor aromatic entity moved around the electron-rich axle. Afterwards, in 2004, the group also succeeded in developing synthetic molecular actuators resembling muscles, contractions, and relaxations, and thus approaching the dream of synthesizing muscle tissues. They gained chemical control over rhotaxine functionalities that translationally moved when triggered by a chemical stimulus, and when attached to gold cantilever, they caused bending movements as a consequence. The field of molecular machines was further developed by introducing the idea of unidirectional rotation about one axis. It was the first time to gain control over the direction of molecular rotation, which represents another breakthrough in this field. So how was this achieved? Well, Fringa and his group succeeded in harvesting UV light and thermal relaxation to cause rotation about a double bond in overcrowded alkenes. Furthermore, they reached a rotational frequency of 12 MHz in 2014. Fringa group also succeeded to unanchor this structure on a gold surface to build a motor-like structure in response to Feynman's proposition about scaling the world to the nano level. They demonstrated the moving action of a chassis-like structure composed of four motor components. Now, if you're wondering why these molecular machines are so important, I can tell you. These tiny machines will revolutionize the industrial world in the 21st century. Indeed, their potential is unimaginable, as said by the Nobel Prize Committee. They will give rise to many applications, just as the invention of the electric motor in the 19th century, that led to the development of electric trains, refrigerators, washing machines, and fans. These magnificent tiny machines can also be used to deliver drugs to specific areas in the body, such as a cancerous tissue. Thus, the damage resulting from the chemotherapy can be significantly reduced. Moreover, these molecular machines can be computerized to construct nanorobots that can function in the human body, so they can detect the occurrence of certain diseases even before the appearance of the symptoms. In addition, they will help develop smart materials that can change in response to different stimuli. Finally, these molecular machines enabled us to answer Richard Feynman's question: how small can we make the machinery? Well, Feynman, we can make them very, very small and very thin, even 1,000 times thinner than our hair.